red planet, so named for the color of the oxidized iron scattered across its crust. Mars is a small, cold world, orbiting our star in a trajectory that occasionally takes it within the outermost edge of the habitable zone. Despite the heat energy from the sun being enough to theoretically sustain liquid water, Mars doesn't have the atmospheric pressure for that. Water on Mars sublimes directly from ice to gas, virtually skipping the liquid phase state. As a result, the yellow sky and the red expanses of rock and rubble that define the Martian landscape are not just cold, they're exceedingly dry. There's a lot of problems caused by the thin Martian atmosphere that would make it exceedingly difficult for life as we know it to exist. The Martian atmosphere is so thin, the atmospheric pressure at the surface is barely 0.6% of the pressure at sea level on Earth. Because there simply isn't enough stuff in the air, heat transfer is virtually non-existent. Here on Earth, our thick atmosphere and our liquid water oceans with their currents will carry and move heat across the planet's surface. But on Mars, there is no thick atmosphere, and there are no oceans. Even the surface layer of the crust has a low heat capacity, so it cools off pretty quickly. There's no major medium to hold heat, and to carry heat across geographic space, so heat can only radiate away. The result is that Mars's climate behaves rather like an earthly desert. The days will get relatively hot, but because there's nothing to hold the heat, when night comes, the temperature rapidly drops. Additionally, because there's no water or air to hold heat and thus to moderate the planet's surface temperature, the winter and the summer seasons experience a very large temperature swing. At the poles, in the dead of winter, in the middle of the night, temperatures can plunge as low as minus 143 degrees Celsius, or minus 225 degrees Fahrenheit. In contrast, at the equator, in the mid-heat of the summer, at high noon, temperatures can be as high as 35 degrees Celsius, or 95 degrees Fahrenheit, which is actually quite comfortable for an unprotected human body. This is also a temperature range where liquid water could feasibly exist, except the pressure on Mars is so low that water can't stay in the liquid phase, it immediately boils away to gas. Mars's thin atmosphere has been caused in large part due to the gases being stripped off the planet and blown away by the solar wind. This, in turn, was only possible because Mars's magnetic field disappeared. The red planet is geologically dead, so there's no magnetosphere protecting it from radiation and charged particles from the sun. This isn't just bad news for the atmosphere, it's bad news for life, because it means the upper 7.5 meters or so of Martian soil has been totally sterilized by solar radiation. The lack of geologic activity also means that there's no volcanoes, and there's no tectonic plates moving around. This means that no new rocks are being formed, and nothing is being subducted back into the mantle, so there's almost a total shutdown in Mars's geochemical cycling. The Phoenix Mars lander, which landed on the red planet in 2008, sampled the Martian soil and found that it was somewhat alkaline, and it included magnesium, chloride, potassium, and sodium. These are all elements necessary for life as we know it, which implies that this Martian soil, when combined with a more fertile, humid, forgiving climate, might have had the capacity to support life. However, the Phoenix lander also found chemicals in the Martian soil called perchlorates, which are chloride-oxygen salts. Subsequent lander missions, like the Curiosity rover, also found perchlorates, suggesting a near-global distribution of these perchlorate salts. This is a big deal, because perchlorates are powerful oxidizers that can do serious damage to cells. More than this, perchlorates can be irradiated, like they would be on Mars, which makes them even more dangerous to cells. And then add on to this the fact that iron oxides and hydrogen peroxide, both of which are really common on the surface of Mars, both of these chemicals react with irradiated perchlorates to make them almost 11 times more deadly to cells. So all of these variables, from the extreme temperature swings, to the solar radiation and the lack of geochemical cycling, to the perchlorate problem, this all makes Mars an unlikely candidate for life. All of these variables put a huge load of stressors on cells, and make it unlikely that a biotic superreaction could be sustained. But Mars wasn't always like this. In fact, the evidence suggests that at some point in its past, Mars was actually much more hospitable, with a denser atmosphere and liquid water in the form of rivers, lakes, and even oceans that would have covered about a third of the planet. This is the proposed explanation for Martian geological history as explained by the Mars ocean hypothesis. This Paleo-ocean is hypothesized to have existed in the earliest days of Mars's history, lasting about 4.1 to 3.8 billion years ago, after the planet had formed and cooled, but before the solar wind had stripped away the atmosphere after the magnetic field collapsed. This Paleo-ocean would have largely filled in the northern hemisphere of the Red Planet, which is characterized by frozen lava flows several miles lower in elevation than the southern half of the planet, which is characterized by highlands. This geography is kind of strange, and if we could see the liquid water oceans on Mars today, it would make for a strikingly dichotomous planet. The North Pole would have been nothing but water, and the South Pole would have been an expanse of frozen Martian desert. There's a decent bundle of evidence to support the Mars ocean hypothesis, including all manner of geological formations on present-day Mars that show clear evidence of erosion from flowing water. In 2007, the Spirit rover discovered an almost pure patch of silica, which was interpreted by NASA as evidence of ancient volcanoes and acid vapors interacting with water. This implies the presence of tectonic activity, and thus, possibly, an active core with a magnetosphere. This would have protected the atmosphere for some time, and maintained enough pressure on the surface to sustain liquid water. It's theorized that in this early, humid Mars, with oceans and a thicker atmosphere, microbial life could have theoretically thrived. This life would have been protected from solar radiation, and it would have access to water and to many of the elements that are necessary for life, or at least for Earth life, including the elements that I already listed, as well as boron and nitrogen. Nitrates have been found on Mars, and this is really exciting because nitrates are a bioavailable form of nitrogen that Earth life, like plants, can metabolically access. Unfortunately for this theoretical Martian life, this comfortable period of Martian history was relatively short-lived. By about 3.8 billion years ago, the core had cooled, and the magnetosphere had dissolved. The oceans boiled away, and solar radiation began an unending cascade into the topsoil, irradiating it into baked sterility. Now, the interesting question that everyone is more concerned with, is there life on Mars today? I've described the Martian environment with its extreme low pressure, its extreme aridity and general chilliness, and of course the solar radiation that's mercilessly decomposing any organic molecules that it can strike. And so with all of this said, where on Mars could there possibly be life? Even though this planet skirts the edge of the habitable zone, it's brutally dry, and in most places, for most of the year, it's fatally cold. A particularly interesting place on Mars is Gale Crater. It's a large crater that formed about 3.5 to 3.8 billion years ago. And in the many eons since the impact, it's apparently been filled in with layer and layer of sediment, perhaps thanks to the presence of an ancient lake that would have slowly dissolved as Mars's atmosphere slipped away. The soils of Gale Crater are typically clays and sulfate minerals, which require liquid water to form. In the ground near and below the crater, erosion patterns are evident in the form of fans and river deltas. The Curiosity rover landed in Gale Crater in 2012, and 2 years later, in 2014, it detected a, quote, tenfold spike, unquote, in methane in the atmosphere. NASA had the Curiosity rover drill into rocks near the areas with these methane spikes, and they found traces of chlorobenzene, which is an aromatic organic molecule composed of a hexene ring bound to a chlorine atom. These findings were really exciting, and scientists suspected that it might be possible that some kind of endolithic life form, some kind of hardy extremophile microbe living in the rock, was producing these organic molecules and methane as a byproduct. This discovery of methane is really cool because of the implications for life. And this wasn't the first time that methane was discovered on Mars either. It was first discovered in 2003 through spectroscopic analysis, and it's been found in other places since, like the Curiosity rover and Gale Crater. It was first discovered in 2003 through spectroscopic analysis. Now, why is the presence of methane so cool? It's because methane naturally breaks down over time, so its presence in the atmosphere suggests that there's some source where methane is actively being produced, at a rate of about 270 tons a year. There have been a number of proposed explanations for this methane, but only a few of them have survived scrutiny. These explanations included everything from asteroid impacts and meteors burning up in the atmosphere to microbial life. Now, many of these proposed explanations haven't held up. Less than 1% of the planet's methane comes from asteroid impacts. Meteors burning up in the atmosphere would produce methane as the heat and/or UV radiation started to affect any organic chemicals in them. But this contribution to Mars would be inconsistent and irregular. One of the last viable explanations is that the methane is a byproduct of microbial life, living deep in the Martian soil or within rocks, like some kind of endolith. In these places, where radiation can't reach, and where there just might be enough heat and pressure for liquid water to exist, there could be life. Researchers have proposed various models for populations and global distributions of methanogens, which are microbes that consume CO2 for carbon and that strip the hydrogen from methane molecules for energy, all without a need for oxygen. Excitingly, the Phoenix lander did some tests on Martian soil and found around 1% perchlorate salt by weight, which is unpleasant, but it's tolerable for methanogens. It's survivable. Other research has found that various species of Earth-based methanogens can survive in low-pressure environments like found on Mars. Because the Martian atmosphere has pretty much no free oxygen and a lot of CO2, there's a virtually endless supply of carbon. It seems that if there is life on Mars, the most likely form that it would take would be hardy methanogenic microbes that live in rocks and deep in the soil, where the solar radiation can't get to them, and where there just might be enough heat and pressure to sustain the liquid water. But this is all in the realm of speculation. Until we can send people to Mars, to take soil samples from deep beneath the crust, and to perform in-depth, long-term analysis, we won't know for sure. The only physical samples of Mars that we have come in the form of 34 meteorites. All of them have been studied pretty extensively, and 3 of them have intriguing details that could be the fossilized remains of Martian microbes. The Shergadi meteorite landed in India in the middle of the 19th century, where it was picked up almost immediately by people who saw its fiery descent. The pyroxene rock showed evidence of water erosion, and inside of it there was morphological evidence suggesting a biofilm, which is a community of microbes that at one time lived in layers within or on the rock to form a slimy layer, or a film, a biofilm. A really mysterious meteorite is Yamato 000593, which landed in Antarctica about 50,000 years ago. This Martian rock also has evidence of water erosion, suggesting that at one point, most likely in its Martian home, it was exposed to moving water. The Yamato meteorite gets really interesting when you zoom in, as NASA scientists found that it contains little bubbles, or spheres, that are filled with carbon. These carbon-rich spheres, according to NASA, could very likely have been generated by biological activity. Now, the most exciting meteor, in my opinion, is the Nakhla Meteorite that fell to Earth in the beginning of the 20th century in Egypt. Decades later, near the end of the century, scientists analyzed the Nakhla Meteorite and found evidence of fossilized nanobacteria. Further study discovered high molecular weight polycyclic aromatic hydrocarbons, which are basically large organic molecules with a ring structure, and this suggests that they were produced by biological reactions. NASA says that up to 75% of these organic molecules, quote, may not be recent terrestrial contamination, unquote. So the case for life on Mars is both exciting and frustrating. Mars is the most Earth-like planet in the solar system, and yet, because it has such a harsh environment, what with the pressure, the dangerous chemicals, and the solar radiation, any life that's native to Mars will almost certainly have to be endolithic, or subterranean microbes, most likely of the extremophile Methanogen variety. For more than a century, we've been getting teased with hints of life on Mars. As far as we can tell, Mars was once a place that could have been thriving with microbial life. But today, the story is different. If we want to find life on Mars, we'll almost certainly have to send some pioneering humans to explore the Red Planet.